Hello everyone and welcome back to another video. Today I'm going to be talking about the concept of infinity in math and what the fuck does it mean? What is infinity? Is infinity a valid concept? Is it valid in math? How do we use it in math? And these are all important questions that I'm sure all of you are asking about math because I know everyone watching my channel is interested in math. But I'm sure after this video you will understand 100% how to think about infinity and mathematics. So let's basically just begin with, what is infinity? Is it a real concept? What does it actually mean? So basically infinity is this idea that the numbers never end, or that there's no end to a certain thing. It's infinite. I think most people understand what the definition of infinity means. We could be really autistic and go look up the dictionary definition, but I think most of you understand like the whole, every single number, there's an infinite number of numbers. Every single number, there's no end to the numbers. Now, is it a valid concept? Is it something that is actually drawn from reality? Is it actually a concept? I would answer no to this, actually. Infinity is not a valid concept, although I think it is useful in math. It's a useful abstraction in certain ways. This idea that the numbers are infinite and that we want to somehow use that fact in math, use this idea of infinity in math, that's actually extremely useful, and I'll get into that more in this video. But the issue is that it has to be used properly. It's really, really fucking easy to basically assume that you can just use infinity in the same way as a normal number and disregard a lot of basic basically when you do so you come to really absurd conclusions, and I'll get into that later in this video. But why do I say that infinity is not a valid concept? Well, primarily because where are concepts derived from? Concepts are derived from reality, obviously. We look at reality, we make integrations, we put things together, we put things in certain categories, omit their measurements, and we say, oh, this is these are books, for example. You see that there's a certain shape, the rectangular shape, that there's a binding, there's pages, but then you omit the measurements, like the certain lengths of the color waves that hit your eyes. You omit those measurements, the certain heights of the books. This is basically Rand's theory of concepts. But ultimately, this is kind of a tangent. We derive this from reality. We have to look at reality, form the concepts, omit measurements. So is infinity a valid concept? Is it derived from reality? Well, to be something that exists in reality, something has to have identity, and this doesn't apply to infinity. Existence is identity. Well, infinity doesn't have an identity. So let's start, I guess, trying to apply an identity to infinity. So what's a really big number? Infinity is the largest number imaginable. If it has an identity, what's a really big number? Well, let's actually do text here, because my handwriting in Paint is terrible. So let's start. Oh, this is a really fucking big number. Oh yeah, look, really big number. Look at how big that number is. Holy crap. Oh my gosh, wow. It doesn't even fit on the whole screen. This is such a big number. Look at how massive this number is. Oh my gosh. So there we go. There's an identity. That's infinity. There you go. The biggest possible number, the highest number imaginable. But wait. There's a bigger number now. And you can keep fucking doing this. And then, oh wait, is that infinity then? No, that's not infinity, because you can keep doing this. You can keep adding a number. You can keep doing that. So infinity is not a valid concept. It's not something that exists in reality. I think most people understand this fact. But this is basically why I would say infinity is not a valid concept. But I'm going to get into why it's useful in math and how to use it in math as well. So let's delete this quick, and let's sort of start with how you can misuse infinity in math. When you can go wrong with infinity. So this is a common instance of someone misusing infinity, and this right here is just notation. This is, for those of you who don't know what this means, basically it's just saying that this is like the term of a function, kind of, and basically you basically sum up every single value of this term from the number k equals 1 to infinity, basically every single number of k, every single value of k. So basically what this means is 1 plus 2 plus 3 plus 4 plus 5 plus 6 forever. Now, Numberphile, a YouTube channel, talked about this. They talked about this sum. and they said it equals negative 1/12. Now think about this. Really, really wrap your mind around what this means. 1 plus 2 plus 3 plus 4 plus all the numbers, all the way up to infinity, equals negative 1/12. This is obviously fucking stupid. This obviously makes no fucking sense. How did they get to this answer? Well, by blatantly disregarding the rules of how you can use infinity in math. Now, actually, as I'll get into later in this video, there's a sense in which this sum is valid. Don't take me very literally here, though. I will explain it later. There's a sense in which there's a reason why they chose negative 1/12, negative 1 over 12. So there's a reason why they did this. But in this video, they were not clear on what that reasoning is, and it made it actually seem like they're saying that adding these numbers together, you add all these numbers together, and you get negative 1 over 12. So let's begin going into this proof. They basically how they sort of do this is they set up a bunch of other sums, a bunch of other infinite sums. They do some manipulations with those, and then they ultimately do a manipulation to prove that it's negative 1 over 12. One thing, we'll get into this later. But let's start with the proof. So they start with this sum, this basic sum. So basically what they're doing here, from k equals 0, so this term in the middle, they're taking it from k equals 0 plus all the way to infinity. So basically what this sum is 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. And they say the sum is 1/2. Now this is obviously absurd as well, because when you think about what the sum is doing, it's going from 1, and then you subtract 1, so it's 0, and then you add 1, so it's 1, and you subtract 1, so it's 0, and it's just alternating between 1 and 0. So when this goes to infinity, it's either going to be 1 or 0, and it basically alternates between the two. So what you're supposed to do in this sense, I guess I should say, is say that this series is divergent, and there's no value for it. There's no actual value for it. But basically what they did is took the average. This is a Cesaro sum. I don't want to get too much into what that means, but it's not the actual sum. This is not actually what this sum equals. So they made a mistake here as well. But once again, it's from a misunderstanding of what infinity is. This is a formula in math for geometric series, which basically if you take a sum where there's a term x to the power of k, you can apply this formula, but only when x is between and not including 1 and negative 1. So the term that they put in for x here is negative 1, as you see. This is not between negative 1 and 1, because with these brackets, the parentheses, it basically implies that you can't include negative 1 and 1 in this, because those series would be divergent. It can't converge to this. I could prove this formula later, but basically what they did is they took this negative 1 in for x. This is one way they could have proved it, with a misunderstanding of infinity, and they could have shown that equals 1 over 2, because 1 over 1 plus or minus negative 1 would be 1 over 1 plus 1, which is 1 over 2. But once again, this is a mistake. They made a mistake here with looking at infinity. And here's the thing: most mathematicians realize they made a mistake. Actually, there's a dude named Mathologer who made a video responding basically to this video and said that, yeah, you completely misunderstood infinity. So if you want even more better mathematical proof of why this is obviously wrong, you can look at his video. He goes into series and divergence and all that sort of stuff, but I'm giving a decent summary here as well. So yeah, let's keep going. I think we understand why this specific thing is wrong, because this is not actually the sum. And what they're doing here, if this is the proof, they didn't actually prove this in the video, which was really blatantly which was really fucking stupid. They should prove everything they're doing here. They should show how they got this number. They basically just said, oh yeah, it's just the average of the two. Let's just assign it the average, which is not how sums work. Think about when you're summing up numbers. You don't find the average of those numbers. When you're adding up 2 plus 3, for example, you're never ever going to say that you're never going to say 2 plus 3 equals the average of 2 and then the average of that and the sum. So you're never going to say 2 plus 3 equals fucking 3.5. That's absurd. That's obviously absurd. You don't say 2 plus 3 equals 3.5. But that's basically what they're doing in this sense with what their sum was here. So that was obviously a mistake. And it seems like this would be how they would prove it. This would be the only sort of legitimate way to prove it. But once again, it's just this sort of rationalistic, oh, we have this formula for when x is between -1 and 1, but not including them. But what if we just plugged in -1? Oh my god, wouldn't that be cool? Wouldn't it be so cool if we could do that? And this is just like, yeah, this is sort of the sense that you get from that Numberphile video, where it's just like, oh my god, I proved that 1 plus 2 plus 3 is -1/12. Oh my gosh, this is so crazy. Math is broken. And it's that sort of attitude that is just so disgusting to me, and yeah, very cringeworthy when it comes to just thinking about mathematics and this absolute disregard for reality and just viewing math as this messing around with symbols. Math refers to something. Math refers to something in reality, and that video completely threw that out the window. So now let's look on the next thing, and I'll explain why this is wrong as well. So here's another sum. Basically, you can look at this and try to figure out what it means, but I also included what it actually means. It's basically 1 minus 2 plus 3 minus 4, and you add all those together. So then what they do, this is a mistake as well. Look at this. They basically are like, we're going to take 2 of these sums, so we're going to add these 2 together, because when you take 2 times something, it's just that thing plus itself again, obviously. So then they're like, okay, let's do that. And basically what they do is they add them together, but they add it in a way where you slide the terms over 1 to the right. And this is a mistake, once again. Let me kind of explain why. You can do this for converging sums, which I'll get into later in the video, I think, when we're talking about how to validly use infinity. You can do this for converging sums, but for diverging sums, this would be a mistake. Actually, let me make sure double check that I'm recording still. Yep. Okay. Good. I got nervous there for a second. But yeah. So let's make sure. Let's explain. Let's see why you can't do this sort of shift with diverging sums. Diverging meaning that these numbers like don't approach 0 as they get bigger. So like 1 minus 2 plus 3 minus 4. These numbers are spreading out, like it's approaching both infinity and negative infinity. But if it were converging, it would be approaching a very specific value. It would be approaching 0, this series. Or the sum would be approaching an actual value. But like the sequence of these numbers, like 1, -2, +3, -4, those numbers would be approaching 0 if we wanted to say that this sum is converging. There's obviously more nuance to this, because there are certain sums that do converge, or there's certain sequences that when summed up, or sequences that converge to 0 that when summed up still diverge. But that's not something that I think is important in this specific video. So let's explain why this way of moving this over is invalid for diverging sums. So let's just let's take this example for here. Let's actually do it with text again. 1 minus 2 plus 3 minus 4 plus 5 minus ... So let's enter here and then space over 1. Or let's just do it like this actually first. 1 minus 2 plus 3 minus 4 plus 5 minus ... So let's pretend for a second like there's some last sort of term here that would be infinity. So let's say plus infinity. Plus infinity. Let's just pretend like this is the case. This is obviously not true. Let's actually just make it a really big number instead, and then we can say plus ... still. Let's just make it 999 just to be whatever. And this would be, yeah, that would be addition. So minus ... So that let's copy paste this and oh, what the fuck? Oh, let's just say like, okay, let's say this get pulled over then. Minus 2 plus 3 minus 4 plus 5 minus dot dot dot. And let's basically just say that, let's do it like this. Let's push this one over 1. So then 1 minus 2 plus 3 minus 4 plus 5 dot minus dot dot dot. And then basically you'll get this added 999 here, and then a subtracted 1,000. And basically the subtracted 1,000 is going to correspond with this plus 999 here. But basically what you're doing, you're adding this extra term in here, and it's a massive fucking term. You're adding this really fucking big term into this summation of the two. And so normally when you would just sum these up, it would just be like in a line, in a line. But now it's like this extra term is getting added into this group, and this sort of continues all the way down. So the further you go, the closer you get to infinity, or infinity as a concept sort of, the further you push this down. But you're going to sort of have to add in this way fucking bigger number, and whatever. It's really imprecise, and I'm not explaining this as well as I would like to, but like, let's imagine that it's a converging series. If it's a converging series, basically this added term would, once it gets to the fucking massive numbers, it's basically 0. It's basically negligible. But this sort of change, this sort of shift in terms makes this change, like, it makes this change really big, and it doesn't work. So basically, the main point of this is basically that you can't do these sort of shifts and sums and all these weird things that you can do with a convergent sum when it's a divergent sum. But they do it here, and that's wrong. You can't do that. You need to exercise caution when you're thinking about infinity, because infinity is not a real concept. And when we're using infinity, we have to exercise the utmost caution with it to make sure that you're using it validly. You're using this concept of infinity in a valid way. But so what they do here is they add these numbers up. They add them up. So it's 1, and then -2 plus 1, -1. And they get this sum again, this sum from earlier. And they're like, oh, this is 1/2. So then they're like, oh, 2 times this second sum is 1/2. So then the second sum is 1/4. Look at that. There we go. We just proved that. We proved that 1 minus 2 plus 3 minus 4 ... equals the 1/4, which is, once again, fucking absurd. But I guess there's a sense in which this one's a little more plausible. I don't know. No, it's still stupid. It doesn't make any sense. So then they're like, okay, now it's time. Now here's the time. Now we can prove that this sum is -1/12. Here we go. Let's go and show that this sum that is obviously going to be positive infinity, assuming that's a valid concept, which it's obviously not. But in sort of shorthand, we're gonna prove that this sum is -1/12. Which is obviously wrong and obviously contradictory. So let's introduce this sum again, this whole sort of sum. Okay, now let's subtract that second sum that we did from earlier, which was the 1 minus 2 plus 3. So then they do that, and term by term they see, oh, this 1 cancels out, and this is just 2 plus 2, 4. The 3 cancels out, and 4 plus 4, 8. And then they realize that, okay, so then we have this sum here, 4 plus 8 plus 12, ... Oh shit, we can factor out a 4 here. Just pull a 4 out of every single one of these things. This is like high school math sort of stuff. I don't feel like I need to explain why you can do that. And then it's like 4, and then it's the same sum pops back up again, and that's 4s. So then s minus the second sum equals 4s. Well then let's just do some algebra quick, and there you go. 3s is -1/4. And this sum is -1/12. After all of this bullshit, after all of these bullshit sort of moves and all this shit that they did with infinity, after all this invalid use of infinity, they got to negative 1 over 12. Now, let's show that this involves a contradiction. Let's prove it. Now, you obviously see that this is wrong. You obviously see this is contradictory on the face of it. But one thing that I'm going to say with this is when you can do these sort of manipulations, these weird manipulations with infinity, you can prove just about anything you want. And because you're not actually adhering to reality, you're just sort of moving around numbers in whatever whimsical way you feel like. And when you do that, you can basically prove anything. So here you go. I'm gonna demonstrate a contradiction here. So basically here is the contradiction. Here's basically the contradiction. It's from a video by Black Pen Red Pen, where he basically shows that this sum is not equal to negative 1 over 12. His video is called Not Negative 1 over 12. This is interesting because it shows that you can show whatever the fuck you want with these infinite sums when you disregard the rules of how to think about and work with infinity, when you treat infinity like it's a valid concept, like it's a valid number. So here we go. This sum again, you guys are familiar with the sum at this point, I hope. Well, then basically what he does here is he groups these groups of 3 into one group. I tried to make it clear with these whole like plus zeros here that he's sort of grouping these numbers together. Now what you see here is that each of these numbers is one above the other, of course. So then you can sort of take from that last number, take from that 4 and give it to the 2, and you realize, oh, it's 3 times 3, which is 9. And you can do the same thing with this one, 3 times 6, which is 18. And do the same thing with the next one, is 3 times 9, which is 27. And what you realize is, these are the multiples of 9. So it's going to be 1 plus 9 plus 18 plus 27 plus 36 plus 45 plus 54 plus ... forever. So then what you realize is, oh, I can factor out a 9 from these, and it's going to be 1 plus 9 times our sum again. Oh my gosh. So then you can do some algebra here, and s equals 1 plus 9s, and then negative 1 equals 8s, because you can move this s over here, move this one over here, and then s equals negative 1 over 8. Negative 1/8. So then we just prove that this sum also equals negative 1/8. Holy shit, this is different from this one. Blatant contradiction here. Obvious contradiction here. This should be obvious to any of you who are seeing this. Negative 1 over 12 cannot equal the same thing as, or this cannot equal both negative 1 over 12 and negative 1 over 8. Everyone should understand this fact. But these two different methods showed that. So let's combine these together and see what sort of interesting things we can prove here. So this equals both negative 1/8 and negative 1/12. So that means negative 8 equals negative 12, and 8 equals 12, 2 equals 3. Oh man, we just proved that 2 equals 3. This is crazy. Look at this crazy math we're doing, guys. Oh my god, this is so crazy. Oh my god. Oh my gosh, we just proved 2 plus 2 equals 5. Oh my god, this is so crazy. Maths is broken, guys. Oh my god. No, this is fucking stupid. This is so fucking stupid. This is obviously wrong, and these are the sort of people that are trying to these are the people on the internet who just are like, they completely disregard math. And I do want to be clear here. Black Pen Red Pen basically made this video to sort of expose this contradiction. So really the people who I'm making fun of here are Numberphile. The people on Numberphile who are like, oh my god, 1 plus 2 plus 3 ... forever equals negative 1 over 12, guys. Maths is broken. Oh my god. Like, oh, good lord. You guys are so fucking cringy, and this is not what math is about. Math is about reality. Math is about looking at reality, and all these stupid fucking games with math it just makes you like, oh my god, aren't we so cool and smart? We're so smart and fucking quirky, and like, good lord. But like, we just fucking proved 2 plus 2 equals 5 here. So this shit is Orwellian. There's a real problem here, guys. Numberphile is trying to make us 1984, guys. This is important. This is fuck. Good lord. It's obviously not that extreme, but we need to have some rigor when it comes to math. We need to think about these concepts correctly. We need to think correctly about these concepts and not just like throw around numbers and explain why like 2 plus 2 can equal 5 now. Good Lord. Yeah. But as I was saying earlier, there's a sense in which this negative 1 over 8 is wrong and this negative 1 over 12 is right. But I don't want to say that, because this shit is not what actually equals the negative 1 over 12. This is a mistake, and I'll explain why they made this mistake later in the video, after we sort of explain how to use infinity validly. But yeah, let's now that we've sort of showed what can go wrong when you use infinity in math, when you think about infinity incorrectly, and there's a lot of things that you can do. You can prove that that there are just as many even numbers in total as the number of natural numbers, but you can also prove that there's 3 times as many natural numbers as even numbers. So you can prove that 3 equals 1 in that sense. But here, let's talk about where infinity is valid here. So let's sort of start with calculus. I'm not going to scroll down too far because I don't want to spoil anything for you guys. But let's start with calculus. So this is a lot of notation here. Some of you will not know what this means. Some of you will. I'll try to explain it as best I can. But this is basically the questions of calculus. This at the end, basically, you want to find the derivative of something. But you need this delta x to equal 0 here. And this is just a function. Let's go and explain this. So the derivative is basically the slope at a specific point of a function. So let's do this. This f of x basically means that when you plug in a certain value for x, you get out a certain value for y. Y would equal f of x here. So this function might look like something like this. Basically every time you plug in a value for x, you get this value of y out. And then every time you plug in like this value, you get this value out. So let's talk about the slope of this line. Let's basically between 2 points. This is let's talk about the slope of this line. Oh, this slope actually like corresponds really well. Let's make it not correspond as well. There we go. Let's say that line looks like that. Now, if you want to find the slope between these 2 points, you have this right here. You have to find this difference, which is delta x. We'll call it that. This is just a name for it. We're just naming it now. And then you have this here. We're gonna call it. Well, let's just say what it is. F of x plus, or that's just f of x actually. Because this is gonna be a negative slope. This is f of x actually. So this point will be x, and this point will be x plus delta x. So then this point right here is going to be f of x plus delta x. Now to find the slope, basically what you do, let's go back to this thing, is take this f of x plus delta x minus this f of x, which is the difference here, the difference between these 2 points, and then divide it by this delta x, this change in x. Now what the derivative does is it makes this delta x into 0. You want to find the point at the slope at a specific point in time. Now this is weird. This is confusing because it's like, because you're like, wait, what the fuck? This there's no change in x and there's no change in y. So how can you find the slope here? What does that even mean? You're finding the slope at a specific point. What does that mean? Well, this is what derivatives are meant to answer, and this is actually really, really important to understand. Just for one application of it, think about, let's pretend like this is a position graph. So like you're moving a certain distance. So like, let's say that this is time, for example. X is going to be time, and then y is going to be your position. Position will be, I don't want to label it as x. That's how position's usually fucking labeled. Let's just call it P or something. I don't know. Y is going to be your position. So then basically you start here, and This is just going to be in 1D space, your position, actually. So you're like, I'm going to start at this point, and then I'll move forward here, and then move back, and yeah. So then basically what this finds, what the derivative is going to find is is going to be your position over your time, which is just your velocity, because it's meters per second, which is, yeah, your velocity. So basically what you want to find is your velocity at that specific point in time, rather than when you're finding a normal velocity, or when you're finding like an average velocity between these 2 points. You just take those points, find the slope between those 2 points, and you see that, oh, this is my average velocity between these two. But this would just be your velocity at that specific point in time, and this is important. This is important in physics and in a lot of applications. So somehow we need this x to be equal to 0. However, that doesn't make sense, because in this sense you're dividing by 0, and it's basically f of x minus f of x. So it's this equation basically becomes 0 divided by 0, and there's no way to assign a value to that. That doesn't make any sense. Well, for one, when you divide something by 0, think about what it would mean. 12 divided by 0. Think about what that would mean. How many zeros does it take to add to get to 12? Well, that doesn't make sense. You keep adding a 0, and you never get any closer to 12. So you'd need like an infinite number of zeros to reach 12, quote unquote. Although that's really imprecise and doesn't actually make a lot of sense, because infinity as a concept doesn't make a lot of sense. So you basically need this delta x, this change in x, to equal 0 here to do calculus. And there's a sense in which infinity is very much involved here, because you're sort of making it infinitely small. You're approaching 0 in this sense. Now let's look at something else. Let's look at the integrals, which is the other thing that I was talking about. The integral is slightly different in this sense. Let's say that this is x. Once again, we'll have it be time for a later analogy. And then your position, or your y, will be... Did I write a y right? I wrote a y wrong. Fuck. I was trying to make that the long leg. The y will be your velocity, actually. So let's draw a similar graph. Let's say it's like this again. And then let's say you have 2 points. Let's call it A and B. Let's just draw lines down, because we're going to do that later anyways. Let's say it's A and you have B. Well, I want to find the area under this curve. I want to find, what is this area? Well, one way you can think about this initially would just be, oh, let's build rectangles here and find each individual area. And basically I'm building them with height at this point for each of them, at the leftmost point for each of these. So then we're going to keep doing that, and eventually we have this area. But this isn't right, because we see that there's this extra area in each of them. So then now we're like, okay, we got to make these smaller. Let's keep making them smaller, and we get closer and closer to the area here. Now eventually what we want to do, well, let's call, actually we're going to call this difference delta x once again. And we know that this delta x, we'll say we divide it into n pieces as well. That's an important thing for this notation back here, for our notation of what we're doing here. So basically, how do you find this area? You find this height, f of x, at this specific point, and then you multiply it by delta x here, and you just add those up. And then for n pieces, basically. So that's what this sum basically means. You have all these points at delta x. You add them up. You add all of them up for n times. For there's n pieces basically, and then you multiply them by delta x. Well, eventually, if we want to get the actual area without these sort of changes, without these sort of differences, we want to let's erase some of this stuff. We want this delta x to be really, really tiny, and almost like to the point where it is like a line. So like it's so small that it's basically a line. this isn't perfect. So this delta x we want it to be 0 if we want this actual area. We want this change in x to be 0. But what would this mean for the n? We need an infinite number of n's. We need an infinite number of pieces of zero width. You basically sum up all of these lines. Now, this isn't possible. This isn't actually possible. We can't actually get this delta x to be 0, and we can't actually get an infinite number of these lines, summing up infinite lines of this length 0. That doesn't make sense. And an infinite number of zeros is still going to be 0. But you want to get this area somehow by summing up these infinitely small pieces an infinite number of times, basically. So how do we do this? I hope this makes sense. Some of this might have gone over your guys' head for those of you who don't know much math, but for those of you who understand this, I think most of you will grasp kind of what I'm getting at. And for those of you who don't, I hope that made a little bit of sense. Basically, the goal. Oh, here, let me explain why this is useful. Why we need to know this sort of thing. Because let's say we have a graph. Like, what's the speed of a certain particle over time? So it's going to be like going fast and then a little slower and then speed up again. That's what this graph would kind of be showing. Now, if we want to find how far that particle travels from time A to time B, we have to basically find the area under that graph, because it's basically velocity times the time here, which is meters per second times seconds. Cancel them out, and you just get meters. So yeah, that's basically why we would need to know that area under that curve. So what's the first sort of solution to this problem? What's the first way that we try to solve this? We have this idea of an infinitesimal. This was our first attempt. Oh, you guys saw it. You guys got a little spoiler there. we had this concept of the infinitesimal. Basically, there's this number that's so close to 0, but it's not quite 0. But it's also the smallest conceivable number. So basically, this idea of an infinitesimal is that it's between 0 and every single positive real number. Now try to think about this for a little bit. What does that mean? That doesn't mean anything, really. Between 0 and every positive real number. Well, every positive real number is greater than 0. But you want this concept, you need something in between the two. Now, what does this concept solve? It basically makes it so that you can put this in for the change in x, and this equation works fine because you're not dividing by 0 anymore, and there still is a slight change in here. So there's still this very small change in x, really, really tiny, and then this really small change in the function of x as well. So you can sort of calculate the slope based on that. And how it solves this basically is that you have these slices that are almost lines, but they're really close to 0. So you don't need an infinite number of slices. So n is not quite infinity. It's just really, really fucking massive. So that's basically what it solves. However, in this sense, you're replacing this concept of infinity that doesn't actually exist with another concept that doesn't exist. So you're basically just making this problem even worse. Let's see why. Let's try to give a identity to the infinitesimal. Let's give an identity to this boy. So what is the smallest number that you can imagine? Let's do the typing thing again. Let's do a really, really small number. 0.00. Let's make this bigger. There we go. 0.00000001. Oh, yeah. This is really small. Is this the infinitesimal? Is this what the infinitesimal is? No, not quite. This is smaller. So is this what the infinitesimal is? Nope. We can make a smaller number. And you can keep doing this, and the infinitesimal just keeps getting smaller and smaller and smaller and smaller here. It's a similar sort of argument to what I did with the infinity thing, where it's like 9999999, that all that shit. And you can just keep coming up with a bigger number. It's a similar sort of thing. So you're basically just replacing one incoherent concept with another incoherent concept. So let's go back to this thing. So this is something that people used for a while. This was the sort of solution for a while. And then we sort of replaced it. We replaced it with this idea of a limit, because you're basically just replacing one non-concept with another. So basically what they do here is say, what is the limit as it approaches 0? you're getting closer and closer and closer to 0, but you don't quite get there. So you're not actually giving it a value. You're not actually giving it this value of the infinitesimal, but you're saying as it gets closer and closer to 0. So it's actually similar to what we were doing here. Let's delete this stuff. It's very similar to what you're doing with that what I was actually doing there with the infinitesimal. When you're taking a limit as it approaches 0, you basically are just plugging in. You're plugging in this really small number for x, and then you basically think, okay, well, let's see. Well, we have that. Well, now let's make it even smaller and smaller and smaller, and see what this function, this value approaches as this becomes 0. And it's the same thing with this integral. You just basically do the same thing, except with the infinity for the n. You plug in infinity for n, and obviously this, as x approaches 0 still, you plug in this infinity value for n, and you're just like, okay, let's just keep making it bigger. So we do this number, and then we're like, okay, we say, okay, that's the value for that. And then now this number, that's the value for that. And you see if it's actually getting closer and closer to a certain number, and you give it that value of what that number gets closer to. So that's basically how we solved that. And that's how you can properly think about infinity. You don't actually use infinity here. You're getting closer and closer to infinity. You're thinking about these really, really big numbers and thinking about, okay, infinity is not actually real. But what happens as this number gets closer and closer to infinity? And that becomes a very useful mathematical abstraction here, because you can find the actual area under curves, and you can find the actual slope at a very specific point, just as these numbers are approaching 0 and infinity in these senses. So that is how you can properly use infinity in the case of calculus. Another way you can properly use infinity is in the case of convergent sums. Earlier we were sort of talking about sums that don't converge. We were talking about the 1 plus 2 plus 3 plus whatever, all the way to infinity. Well, here you can actually solve a convergent sum. Now there's a reason why you can do this. You can I can kind of pull that up here. Let's move this, actually. Let's get this shit out of the way. You know what, let's just delete it. So actually, let's think about the sum for a little bit. This is basically what Zeno's paradox is. It's a half plus a fourth plus an eighth plus ... all the way to the infinitely big k's, all the way to these infinitely big k's. So what does this approach? Well, once you get all the way out to really big numbers, this number is pretty much 0. The value of this term will be pretty much 0. So at that point, you're basically adding a bunch of zeros at the end. And what does this number approach? Well, this number gets very close to 2 as this k approaches infinity. So this is a valid way to use infinity here as well. To find the answer to these sort of sums, you can find, okay, as this limit approaches infinity, because you're using limits here as well. Limits are a valid way to use infinity. That's basically how you can use infinity properly. You see that as this k approaches infinity, it equals 0. So when you get to these really big numbers, this number gets so small that it's 0. So when you actually get to infinity, quote unquote, which is a concept that doesn't exist, that number is going to be 0. You're going to add 0 once you reach infinity. So you're going to get 2 basically. This is really abstract, but this is basically the point that I'm trying to make here. So let's go back to the negative 1 over 12 sum and try to understand why that makes sense. Why they would have used that value for this. So I know you guys see this complicated shit down here, I honestly don't understand what this means exactly or how that's proved, but this is something from higher level math, obviously. So let's start just understanding what this means. This basically, there's a sum called the Riemann zeta function, and at the value of negative 1, this value is negative 1 over 12. So what is the Riemann zeta function? Well, one way that we can think about what this function actually is, there's actually a really complicated definition that involves like the gamma function and integrals and stuff like that. But one way that we can think about this is just for all values when you plug in a number greater than 1, it's the sum of 1 over k to the power of s, which is basically here. Let's type this out actually. Which equals 1, or here, let's do this. 1 over 1 to that power of s that we were talking about before, and then you just keep basically doing this all the way to infinity at this thing. 1 over 2 to the s, and then you just basically keep adding that. So that's basically what that means. And so basically this only makes sense for s's that are greater than 1. This only actually makes sense because that's the only time where these values will actually converge to any number in particular. So let's basically start with talking about that. So we basically know that when this is -1, this is something that's proven by higher level math, that this function actually equals -1 over 12. So basically what these people did, this is the reason why they can find that why they can say that this absurd statement, this is the reason why they said it, that this 1 plus 2 plus 3 plus 4, whatever, all the way to infinity is -1 over 12. The reason why they tried to say that is because when you plug in -1 for this function, what you get is this sum. You get this 1 plus 2 plus 3 sum. Well, this Riemann zeta function, when it's -1, it's -1 over 12. So this is why they chose -1 over 12 to solve for in this thing, and that's why they didn't choose -1 over 8 like black pen, red pen did. So they used this fact about the Riemann zeta function. They basically used these two facts to make this rationalistic assertion. Actually, this is very rationalistic here. This is a very rationalistic assertion here. They're like, okay, well, we know that this is true for the Riemann zeta function, and we also know that this is true for the Riemann zeta function. So let's just combine the two facts and say this sum equals -1 over 12. Well, the issue is they completely ignored the fact that when this only applies when s is greater than 1. This only makes sense when s is larger than 1. That's the only time that this sum actually makes any sense. This is the only time that sum actually converges to a number. Let's basically figure out where does this -1 thing come from. So there's this there's this thing called analytic continuation, which I don't fully understand, but they did this on the Riemann zeta function. If you actually want to watch a video about that, there's a 3 blue 1 brown video on the Riemann zeta function and why they can analytically continue it and why they can extend it to these negative numbers, and how they did it and why there's really only one specific way you can extend it to these negative numbers. But this is how they do it. This is how mathematicians do this. Basically, let's plug in -1. So you have to have s equals 2, plug it in, and it's -1. And you basically can solve all of this. You prove that it that this equals this. It's going to equal this, and then cosine of. So you have each of these terms in here. So this part comes from this part when you plug in the 2. This part comes from the cosine. This gamma of 2 comes from here. This Riemann zeta of 2 comes from here. And then here's basically an explanation. The cosine of pi is going to be -1. The gamma of 2, well, the gamma of 2 is just gamma. Gamma of x is just x minus 1 factorial. So then gamma of 2 is just 2 minus 1 factorial, which is just 1 because factorial is like the number times the lower number times the lower number all the way down to 1. So it's just 1 factorial 1. Yeah. And the Riemann zeta function of 2, we'll just plug in 2 into this formula that we had before, and we see that it's pi squared over 6, which is the Basel problem, which is what Euler solved and made Euler sort of famous. So then you plug all these back in, and you realize that the Riemann zeta function at -1 equals -1 over 12. Now, I want to be very fucking clear here that this does not mean that this sum equals -1 over 12. That is so wrong to think that way, because it's obviously untrue. You need to exercise caution with math. Math refers to something in reality, and this Riemann zeta function, it's certainly probably useful. I don't know the exact uses for it right now because I'm not at that level of math. But this Riemann zeta function is something that has been analytically continued, and it has a certain value at -1, with -1 over 12. But this does not mean that the way that because we can approximate, or we can, the Riemann zeta function for numbers above 1 is defined by this, it doesn't mean that for numbers below 1 it's also defined by that. That's obviously a leap in logic. You can't do that with infinity. Infinity is a complicated number, and you can't say that it equals negative 1 over 12 after the sum. Now, I want to be clear that there's a sense in which it does, and this is the sense. This is the sense in which it does, because the Riemann zeta function is this sum, and at negative 1, this sum would look like this, and at negative 1, the Riemann zeta function equals negative 1 over 12. So there's a sense in which that sum does. But this number file video was completely unclear on what that actually means. I don't think it mentioned the Riemann zeta function. It made it seem like this sum actually equals negative 1 over 12. Now, anyone who can think, anyone who can understand reality, anyone who can look at reality sees that this is untrue, sees that this is completely false. But it makes it, when you do these sort of things, it makes it so that people are like, wait, so these guys are smarter though. These guys understand math. So like maybe my intuitions are just wrong. Maybe my sense data is just wrong. And this sort of shit leads to skepticism. This sort of stuff leads to people being skeptics. And they're like, maybe these people just know things that I don't understand. But yeah, so this Riemann zeta function at negative 1 equals negative 1 over 12. You don't need to understand why it does. I don't fully understand why it does either. I'm not that high of a level of math yet. But just because that's true doesn't mean that this shit is true. That doesn't, yeah. that's obviously a rationalistic jump. And I think people should understand that. And here's actually a video on the Riemann zeta function by 3blue1brown. I'll click on this quick, actually. Click the link. Let's see if it loads. Keemstar and Drama. I've been watching Leafy a lot. Yeah, so this video basically goes through and explains how this works, this analytic continuation stuff. But yeah, that's basically what it does. It explains how this analytic continuation stuff works, and it has some really beautiful diagrams. Yeah, very, very fucking beautiful diagrams. This one actually doesn't look very good. That was he was just showing that there's other ways that you could possibly think about extending it. Let's look at this one actually. Yeah, so he's sort of extending it at this point. Yeah. So basically here we go. Yeah, so basically he goes through and explains that. I'll post the link down there in the description, and you guys can watch that video if you're interested in this more. But yeah, he had a really good video there, and this sort of thing just shows the importance of thinking about math as something that adheres to reality, as something that has to conform to reality. You can't use math to contradict your sense experience. You can't use math to say things that aren't true. You have to be very strict about adhering to reality when thinking about math. Now you can show certain things are true, like this Riemann zeta function, but you have to make sure that it's something that adheres to reality and not make leaps in logic that make it seem so that something that is clearly untrue in reality is actually true in reality because of something new that you've discovered, or something new that you've induced or deduced, or one of the two. Because I think most of math is done through deduction. But yeah. So, yeah, that's basically all that I have to say about this. Math and infinity is a really, really important thing in mathematics. But one needs to be very, very careful with it, so not to lead to absurd conclusions. But yeah, be careful with infinity and use it. Be fine using it. Use it in the context of limits though, because infinity doesn't exist. Infinity is not a real thing. But numbers can approach infinity, and once you understand that, you'll understand a lot more about mathematics and what certain concepts in math mean and how infinity is properly used in math. Most mathematicians are decent on this, but the problem comes when people try to pretend as if infinity is a real concept and that you can do the same things that you can do with any other numbers that you can do with infinity. Because when you do that, you can prove really absurd things. Now it may feel really cool to show that 2 + 2 = 5, but if you think that, you're a fucking nerd and you're fucking cringe. Sorry. That's a joke. No, it's okay. It's okay. Don't leave my channel. Don't unsubscribe. I love everybody. I love everybody equally. Everybody is loved by me. Everybody is equal. Everybody is the exact same in every way, and I don't judge anyone. We all know this. But yeah, don't be cringe. Don't be cringe. 2 + 2 does not equal 5. You know this. Look at reality. Look at this. Look at this shit. I have 2 shoes and 2 shoes. Do I have 5 shoes? No, I have 4 shoes. There you go. I just proved this. I proved number file wrong, boys. But yeah, I think that's all I have to say for today. So thank you all for watching, and I hope to see you all in the next video.